In this video, we'll look at graphing cosecant, secant, and cotangent. So you have to remember when we're graphing these that these trigonometric functions are the reciprocals of sine, cosine, and tangent respectively. So we'll go through graphing cosecant, secant, and cotangent, and then we'll talk about amplitude, period, and transformations. And I've got a little bit of integration of another kind of technology online learning resource that will be really useful for you all. So to begin, like we did last time, I think it'll be really useful for us to just come up with all of these coordinate pairs. So we'll start with cosecant. Remember from the last video, cosecant t is defined as 1 over y. So that's the reciprocal of sine t, which is just y. So cosecant of 0, we have to look at t equals 0. That's 1 over 0. So we've already got a problem, but we'll write undefined there. So remember, whenever we have an undefined, that's going to mean an asymptote. So keep that in the back of your head. Moving along, the counterclockwise direction of the unit circle, cosecant of pi over 6, we grab 1 over 1/2. So that'll give us just 2. So we're starting up at infinity, and we're getting less big as we go along the outer edge of the unit circle. Cosecant of pi over 4, that's 1 over root 2 over 2, which that'll simplify down to root 2. So we have 1 over root 2 over 2, which then flips and multiplies, so that becomes 2 over root 2. And then that, if you rationalize that, when you multiply by root 2 over root 2, it simplifies down to root 2. So we have root 2 there. Cosecant of pi over 3, that's 1 over root 3 over 2, and that should simplify to 2 root 3 over 3. Cosecant of pi over 2, that gives us just 1. And now I think we'll start going in the opposite direction. We'll start getting bigger again after pi over 2. So we'll hit 2 root 3 over 3 for 2 pi over 3. Then we'll hit root 2, 2, and once we hit pi again, we're undefined. So to summarize this, we start really big, we get smaller and smaller and smaller until we hit 1, then we get really, really big again. So you can imagine that once we hit the bottom half of the unit circle, all of these values will go negative. So then we'll flip down to start at negative infinity, increase up to -1, and then go back down to negative infinity. Moving on to secant, we start at 1 over 1 for secant of 0, so that's a good place to begin. Then moving over to pi over 6, we get a little bit bigger, so we hit 2 root 3 over 3. Remember, that's the simplification of 1 over root 3 over 2. Then we'll get to root 2. Since cosecant and secant are very related functions, just as sine and cosine are, sine and cosine take on the same value at pi over 4, just like cosecant and secant does. So that should explain to you why secant of pi over 4 is root 2. Then secant of pi over 3, that's 1 over 2, so we hit 2. And then as we approach secant of pi over 2, that'll go up to positive infinity, so that'll be undefined. Now on the left half of the unit circle, we have negative x values, so we should flip down for these next ones. So we'll have secant of 2 pi over 3, which will be 1 over -1/2, so that simplifies to -2. Then secant of 3 pi over 4, that'll simplify negative root 2. Then -2 over root 3, or -2 root 3 over 2, and then secant of pi gives us -1. Similar kind of pattern, right? Like if we think about what we've got in our head so far for cosecant, we've got like half of the cosecant, so it's a little bit translated just like sine and cosine are, so those are very related functions again. So moving on to cotangent. Cotangent of 0 gives us x over y. So we've got 1 over 0, which that's going to be undefined. Moving on to cotangent of pi over 6, that's root 3 over 2 over 1 over 2, which that should just be root 3. The denominator and the numerator and the denominator are both 2, so those will cancel. Cotangent of pi over 4 gives us a 1. Cotangent of pi over 3, so that'll be x over y, 1/2 over root 3 over 2. So again, the denominator and the numerator and the denominator will both cancel out. So we'll have 1 over root 3, which then if we rationalize that, we end up with root 3 over 3. As we approach pi over 2, cotangent of pi over 2, that's x over y, 0 over 1, so that gives us 0. And now, just like we had with tangent, once we move to the left half of the unit circle, the sign's going to flip. So now we'll have all these same values, just negative. So I have negative root 3 over 3, negative 1, negative root 3, and then as we approach pi, we'll go undefined. Okay, so we have all of these coordinate pairs. Now let's graph them. So we'll begin with cosecant. So at 0, we're undefined. That should tell us we have an asymptote. At pi over 6, we hit 2, so that's like right about there. Pi over 4, we're at root 2. Remember, root 2 is a little bit above 1. Pi over 3, 2 root 3 over 3, that'll keep bringing us down flatter and flatter, and then pi over 2, we hit 1. Then we go in the opposite direction. So we have this coordinate, and as we approach pi, we again go undefined. So I've got to draw another asymptote there. And this is what cosecant looks like. Just like that. And then, like we said earlier, since now we're moving on to the bottom half of the unit circle, we'll take on the same values, just negative. So we can draw a few of these here. We'll go here and here, and we'll look like this. And then, since we have this asymptote here, now that we're kind of moving back around to the positive y side of the unit circle, the top half of the unit circle will become positive again. This should tell you that cosecant has a period 2 pi. P equals 2 pi. So it repeats itself every 2 pi units, and then we can draw the second half of our graph. So for cosecant, the parts of the graph that's defined, these are going to be very kind of U-shaped graphs. Not quite parabolic, not quite, rectangular, but somewhere in between. Moving on to secant. So at 0, we start at 1. And then as we move in the positive direction, counterclockwise around the unit circle, we'll hit this value here, the same one as secant. And then here, and as we approach pi over 2, we go undefined. So now we have an asymptote at pi over 2 for secant. So if we go the negative direction along the unit circle, since we're still in the right half of the unit circle, we have more positive values until we hit negative pi over 2. So now we have this. Again, you can see that there's this relationship between secant and cosecant. That if we shift secant pi over 2 units to the right, we end up with cosecant. And similarly, if we shift cosecant pi over 2 units to the left, we end up with secant. Now we'll finish off drawing the graph. I'll go ahead and put in these other asymptotes for secant. I won't bother drawing the half parts of the graph. So similar to cosecant, secant also has a period of 2 pi. Now, last but not least, for cotangent, this one, you'll again see the relationship between cotangent and tangent as we graph it. So at 0, we have a similar asymptote to cosecant. Then, as we leave the positive side, so since we're positive at pi over 6, that should tell you that as we approach 0 from the positive half of the graph, we go up to positive infinity, something to keep in the back of your head. So at pi over 6, we're at about root 3, and the square root of 3 is about 1.7. So I'll draw that right about there. And then we hit pi over 4, we're down at 1. At pi over 3, we're at root 3 over 3, which should be less than that, so we'll just keep kind of traveling along here. Pi over 2 we hit 0, and then we take on the similar kind of values. So here, 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 and then once we approach pi, we're again hitting this asymptote. So cotangent looks like that. So that looks a whole lot like tangent, right? In fact, it looks like if we flipped tangent over the x-axis. And that should make sense, right? Because we're just flipping the x and y ratio. Tangent's y over x, cotangent's x over y. Then we would have to shift it over just a little bit, right? Because tangent goes through the point 0, 0. So there's this relationship between cotangent and tangent, just as there's this relationship between secant and cosine and sine. That is, it's a translation of one to the other. So then the remaining bits of the graph, we'd again have an asymptote at 2 pi and negative 2 pi, and then like tangent, cotangent is pi periodic. So then we could draw in a copy of what we've already drawn, right here, like that. Here and here. So those are your graphs of cosecant, secant, and cotangent. Noting now that we see what they look like, we can see that cosecant is 2 pi periodic, secant is 2 pi periodic, and cotangent is pi periodic. So that leads us to the next part. Amplitude, period, and transformations. The graphs of the trigonometric functions y equals a cosecant k, x minus b, plus c, y equals a secant k times the quantity x minus b plus c, and y equals a cotangent k times the quantity x minus b plus c, all for k greater than 0, have amplitude a, horizontal shift b, vertical shift c. Cosecant and secant have period 2 pi over k, just like sine and cosine do, and cotangent has period pi over k, just like tangent does. So now with this, so we can see it, I will slide over, and I've graphed cosecant with our general form in Desmos. Now I've also done all of the asymptotes, so you can see the blue dashed lines are the asymptotes at 0, negative pi, pi, etc. for the graph of cosecant. Now, like we discussed before, if I modify k, if I increase k, that should compress the graph of cosecant, because we're shortening the period of the function. By definition, cosecant's period is 2 pi over k, so if k gets larger, then the period gets smaller. Just like that. And again, if we decrease k, the period will get larger. Very slowly, like that. So I'll make this back, I'll turn this k back to 1. So k is 1. Back to our standard form of the function. A again is the amplitude. Now, in this case, remember when we talk about changing the amplitude of the function, we're kind of pulling away from the x-axis. Same thing happens here. In this case, I want you all to think of pi over 2 and 1 as your kind of anchor points. So those values, those y values, will all increase. So as a gets larger, the function kind of pulls away from the x-axis, and similarly, as a gets smaller, it gets really close to the x-axis. Of course, if a goes negative, it'll flip over the x-axis and then pull away. So you can see that. Make a 1 again. So like before, if we change b in the positive direction, so if we increase b above 0, we're going to be moving towards the right, towards the positive x side. So increasing b, and you can see the asymptotes move with it, really important. And if we decrease b, we'll move in the negative direction. Again, the asymptotes move with it. Reset this back to standard form. And then for C, we're just changing kind of the midline of the function in a sense. So in this case, with the standard form of cosecant, we've got a midline about the x-axis, right? It's reflected in a sense about the x-axis. So if I increase C, I'm kind of shifting the midline upwards. So you can kind of see if I increase C, the whole graph increases upwards, but we've still got this difference of 2 units between the top of the left of the bottom out U, the downwards opening U, and the bottom of the right upwards opening U. So it all kind of shifts up and down together. So there you go, there's your summary. So A kind of pulls the graph away from the x-axis. K changes the period. Increasing K makes the period smaller, and decreasing K makes the period bigger. Changing B will just move everything to the right or to the left. And changing C, we're moving the whole thing, including this midline between the top half of the graph and the bottom half of the graph. We're moving that all up or down. So changing the amplitude, changing the period, changing its position left to right, and changing its position up and down. So that's amplitude, period, and transformations. In the next video, we'll begin to look at some interesting properties and relations of the 6 trigonometric functions: sine, cosine, tangent, and cosecant, secant, and cotangent.